Most prospectors walk right past it. A fist-sized chunk of milky quartz lying inert among river stones gets kicked aside without a second glance. Yet in certain terrains, that same piece could mark the invisible tail of a mineralized vein system. One that once carried both gold and diamond indicator minerals into ancient alluvial traps. The real clue is not the quartz itself, but where it ends up. In river systems that cut through metamorphic or greenstone-hosted terrain, quartz float is often a lag mineral, resistant to erosion, heavy enough to settle with other coarse debris, but light enough to drift further than gold or chromite. When you see it nestled above a tailout or behind a midstream boulder, it's acting like a breadcrumb dropped by retreating hydrothermal systems. It wasn't the target, but it knows the way. The key mistake many make is assuming quartz is too common to matter. While true that quartz comprises a huge percentage of crustal silica, only a small subset comes from mineralized fluid systems. These carry the thermal and chemical energy to transport gold as complexes or to fracture host rocks near kimberlite intrusions. In these cases, quartz often forms as gangue in veins or as overgrowth on pre-existing structures, evidence of past events that matter now. What matters in the field is association. If quartz appears with angular shapes, stained edges, or adherent iron oxide, that's a clue it didn't come from far. Rounded, pure white quartz tends to come from eroded sedimentary formations, usually barren, but angular, iron-stained quartz with inclusions may have been freshly weathered from a host that saw hydrothermal transport. If you see that alongside ilmenite, pyrope garnet, or black sands, it's no longer background noise, it's directional evidence. What makes quartz even more potent is how it behaves in low-flow environments. In flood zones or ancient channels, heavier particles like gold or chromite drop out earlier, but quartz lingers further, settling in meanders or behind obstructions. So when quartz appears with heavies in the same pan, you're near the convergence zone, what some call the pay line. That intersection is often only a few meters wide, but can carry the richest concentrations of multi-mineral value. The real test begins by learning to separate signal from noise. When is quartz a clue, and when is it a distraction? The answer lies in its look, feel, and neighbors, which leads us to the next critical distinction: what real indicator quartz looks like, and how to pick it from the crowd. Not all quartz is created equal, and in the field, knowing which pieces speak and which stay silent can change everything. One small inclusion or fracture pattern can mean the difference between inert debris and a signal worth chasing. Most quartz is too clean, too perfect. What you're looking for is the story told by imperfections. Start with luster. Field quartz. From mineralized zones often has a dull to greasy appearance, especially when weathered. This contrasts with the glassy luster of water-worn vein quartz, which tends to have a sugary or smooth break. More telling is the presence of embedded minerals, tiny pyrite flecks, fine tourmaline needles, or red-brown garnet grains caught in fractures. These aren't random. They're signature traits of a quartz that formed alongside high-temperature, hydrothermal fluids, capable of transporting gold, silver, and base metals. Color is another tell, but not in the way most expect. While crystal-clear quartz is often prized for aesthetics, it usually lacks mineralization. The quartz you want to see is milky or smoky, with ghost zoning or cloud-like inclusions. Milky quartz often forms when fluids cool rapidly, trapping microbubbles and suspending minerals in solution. Smoky quartz can indicate exposure to radiation, often associated with granite-hosted systems where uranium and thorium are present, contexts that also favor accessory gold and rare earth elements. Fractures matter more than size. Look for healed breaks, areas where the quartz cracked and then resealed under pressure. These zones can host fine sulfides, creating what prospectors call sugar veins, small, granular pockets rich in metallic traces. You'll also want to examine contact textures. Where quartz is fused to country rock or encloses fragments of schist, greenstone, or serpentinite, it's a sign of structural emplacement rather than simple precipitation. One underused trick is checking for iron staining. When quartz hosts even trace sulfides, weathering releases iron, which then leaches out as rust-colored streaks or halos. A reddish-orange blush, especially near fracture points, is often a stronger clue than any visible metal. Even after years of exposure, this stain clings to quartz like a fingerprint of past chemistry. In known gold or diamond terrains, this level of detail adds up. In British Columbia's placer belts, milky quartz cobbles with black tourmaline threads are a common companion to gold streaks. In Western Australia's craton margins, angular quartz fragments peppered with magnetite or ilmenite often appear just upstream from alluvial diamond finds. The trick is recognizing that quartz is rarely alone, and when it carries baggage, that's your trailhead. But all this assumes the quartz is native to the spot. What if it moved? That's the next trap to navigate. Understanding whether you're reading a float trail or standing directly on top of something worth breaking open. A narrow quartz vein cutting across a bedrock face may seem like a jackpot, but veins are deceptive. Some carry immense mineral wealth, others are sterile. The difference lies in structural context and mineral chemistry, clues the surface doesn't give up easily. More than a few miners have chased gleaming quartz walls deep into the earth, only to find they were following a barren feeder vein, not the main ore chute. Hydrothermal quartz veins form when mineral-laden fluids penetrate rock fractures and precipitate silica under pressure. But only when these fluids also carry elements like gold, silver, or base metals, and only when cooling and chemical triggers align do they leave behind economic concentrations. Otherwise, the quartz seals. The kraken moves on, leaving a white scar in the rock and nothing more. So how do you tell a live vein from a dead one? Start with structural intersections. Productive veins often run perpendicular or oblique to major faults or shear zones, places where rock has fractured repeatedly over time. If a quartz vein cuts across a known deformation belt or is flanked by parallel fractures, that's a strong structural sign. The most promising veins often form in the dilation zones, where multiple stress fields intersect, allowing space for fluids to pool and drop load. Next, look for wall rock alteration. A productive vein changes the rock around it through heat, fluids, and chemical exchange. If the quartz is bordered by bleached, iron-streaked, or clay-altered host rock, it's been part of a fluid-rich system. Even subtle changes, such as mica growth or dark haloing, indicate hydrothermal activity that could mean more than just silica. Then there's the matter of inclusions. Quartz veins with fine-grained sulfides, especially pyrite, chalcopyrite, galena or arsenopyrite, deserve extra scrutiny. These minerals don't form in isolation. They suggest gold may be locked in microfractures or bound within sulfide matrices. Sometimes these inclusions are not visible to the naked eye, but can be detected with a strong loupe under good light. Pay attention to sooty zones or metallic flecks aligned along growth planes. But perhaps the most misleading signal is vein size. Large, clean quartz veins often grab attention, yet many of the richest deposits are found in veins less than a meter thick. These are frequently tension gashes, short-lived, high-flow paths that concentrate metals efficiently. Massive quartz veins can simply be silica dumps, formed when fluids cooled too fast or lost chemistry before reaching ore saturation. Don't chase size, chase evidence of mineral transport. In diamond-bearing contexts, quartz veins are rarer, but still diagnostic. A quartz vein intersecting a serpentinized ultramafic intrusion is unusual and could indicate that fluids interacted with deeper mantle rocks, bringing up more than just silica. Some of the most promising diamond indicator terrains in South Africa and Siberia feature rare quartz stringers near or within kimberlite pipes, often in heavily altered zones. Ultimately, quartz veins are signposts, not guarantees. The trick is knowing when they point towards something deeper, or when they're relics of a system long spent. And to do that, you'll need to understand their position in the field, whether they're rooted in place or riding loose as drifted float, because only one leads you back to source. It's one of the simplest yet most consequential distinctions. In fieldwork, are the quartz fragments under your feet in place or have they traveled? Mistaking float for source has misled generations of prospectors, sending them digging into dead ground or abandoning what was actually close to a rich vein system. Float quartz refers to fragments that have broken off from a parent vein or outcrop and been transported downhill or downstream by gravity, water, or glacial movement. These pieces can show all the desirable traits, inclusions, staining, sulfide stringers, but if they're far from source, they don't mark a dig site, they mark a direction. The diagnostic task becomes one of vectoring, working backward from float dispersion to locate the origin point. In contrast, in situ or in-place quartz is found within or adjacent to bedrock, typically showing a structural relationship to surrounding rock. Angularity is one clue. Float tends to be more rounded from transport, while in-place quartz is often sharply fractured, locked into joints or fissures. Fresh breaks with crisp edges and little lichen suggest minimal weathering, another sign of proximity to source. Elevation and slope offer context. If quartz is scattered across a slope without obvious origin above, it likely came from somewhere. Upslope, possibly transported during freeze-thaw or erosional slides. On ridgelines or benches, quartz with no uphill source is more likely to be close to origin. Drainages complicate the picture, especially in glaciated or alluvial environments, where materials can travel kilometers from their starting point. That's where systematic gridding and float tracking come into play. One method involves mapping quartz float density using GPS and plotting dispersal patterns. High concentrations of angular float aligned along contour breaks can form dispersion. Drains, these typically widen downslope from the source, forming a fan-like pattern. By collecting and characterizing float at regular intervals, examining each piece for luster, inclusions, and associated minerals, you can follow the train back to its apex. That apex, especially if marked by embedded fragments or rootless veins in outcrop, often indicates the presence of a buried system. In diamond terrains, float can be particularly misleading. Kimberlite pipes often weather into soft clays that disperse poorly, but associated material like ilmenite or garnet may still migrate. Quartz float found alongside these indicators should be treated carefully. In some cases, it may have entered the environment from later hydrothermal events, not the primary magmatic intrusion. Yet, when quartz float consistently appears alongside pyrope garnets, chromite, or magnetite in a defined slope corridor, it becomes more than a coincidence. It's a convergence clue. Adding to the complexity is the role of paleo channels. In ancient buried river systems, quartz float can become entombed in old gravels, separated from its original context by thousands of years and meters of overburden. In such cases, finding quartz in modern cuts or erosion gullies may actually point to deeper, older systems, a layered history that rewards those who can read the terrain in 4 dimensions. To narrow your search, the next move is to study what comes with the quartz. Because while quartz can lead you close, it rarely travels alone, and its companions often speak louder than it does. Quartz alone might whisper, its companions shout. When fragments of quartz appear alongside specific accessory minerals, particularly pyrite, garnet, and black tourmaline, it's a shift in signal strength. These aren't decorative additions. They are diagnostic indicators of past fluid systems capable of concentrating precious and industrial minerals, including gold and diamond pathfinders. Let's start with pyrite. In many auriferous systems, pyrite is more than an incidental inclusion. It's a transport partner. Gold often forms microscopic associations with pyrite, either in solid solution or as invisible inclusions along growth planes. When you find quartz with well-formed cubic or framboidal pyrite, especially near fractures or in sugar-textured quartz veins, it's not just iron sulfide, it's a fingerprint of thermal and chemical conditions that favor gold deposition. But pyrite oxidizes. In weathered float, what remains is the rusty halo, the iron staining or gossan that coats quartz surfaces or seeps into fractures. Don't discard a quartz piece for lack of visible pyrite. Look for yellow-brown streaks or deep red-orange mineral films. In some cases, even a light scratch with a knife can reveal residual sulfide under weathered crust. This is especially true in metamorphic belts, where pyrite was intergrown with gold, like parts of the Abitibi Greenstone Belt or Ghana's Birimian formations. Garnet adds a different layer. Not all garnets matter for gold or diamond hunting, but specific types do. Almandine garnet, deep red and often fractured or zoned, is frequently associated with high-grade metamorphic rocks that also host quartz gold vein systems. In contrast, pyrope garnet, purplish and higher in magnesium, is a key diamond indicator mineral. When you find either type embedded in quartz or appearing in the same concentrate as angular quartz fragments, that's a moment to pause. Look at garnet habit and hardness. Pyrope tends to form dodecahedral crystals and is noticeably denser and harder than almandine. It resists scratching by steel, has a higher specific gravity, around 3.84.2, and won't fracture as easily under pressure. If you're finding these garnets near quartz float on serpentinized terrain, especially with chromite or ilmenite present, your odds of being in a diamondiferous context increase. Then there's tourmaline, particularly the black prismatic variety, known as schorl. Tourmaline forms in boron-rich hydrothermal systems and often signals late-stage mineralizing fluids. It's commonly associated with tin, tungsten, and gold in granite-hosted systems. When black tourmaline appears as radiating clusters within or adjacent to quartz veins, especially in grisonized granite or pegmatite systems, it's a direct link to the thermal history of that terrain. What binds these companions is not just co-location, but co-formation. If you're pulling quartz, pyrite, garnet, and tourmaline from the same slope or stream tail, they likely rode the same fluids or weathered from the same source zone. This is especially powerful when they concentrate together in pan or sluice. Seeing black tourmaline needles trapped with fine gold or finding garnet and quartz in the same riffle pocket isn't coincidence. It's gravity sorting from a shared release point. In some Brazilian garimpos, entire dig sites are staked on. The co-occurrence of quartz with ilmenite, garnet, and serpentinized rock fragments. The logic is consistent across continents. Certain minerals are geochemical markers of deeper, hotter, and potentially diamondiferous systems. When they migrate, with quartz, they act as vectors, not just artifacts. Still, where they settle tells just as much as what they are. And the next stage in the hunt brings us to a deceptively quiet place in the river system, where energy drops and hidden values collect. It's easy to focus upstream, chasing bedrock, hunting veins, but downstream holds its own secrets. In particular, the inside bend of a meandering stream or the tailout at the end of a riffle run often hides more than just water-worn pebbles. These slow-flow zones are natural concentrators, sorting materials by weight, shape, and density. And when quartz begins to show up there alongside heavy minerals, you may be standing on a silent golden diamond trap. Here's how it works. As water flows around a bend, its velocity changes, fast on the outside curve, slow on the inside. That drop in energy creates a deposition zone. Heavier particles like gold, magnetite, ilmenite, and even diamonds settle here, but so do quartz fragments if they're the right type. Quartz is lighter than these true heavies, Sg 2.65 versus gold's 19.3 or diamond's 3.5, so it doesn't always stay put. When it does, it's a clue that flow was slow enough and that you're close to a high-density release zone. Look for angular quartz fragments mixed in with black sands or garnet grains on inside bends or below sudden gradient drops. In productive terrains, these locations often build up as quiet pockets beneath root mats, behind boulders, or just below a lip in the bedrock. Even shallow gravels, under 30 cm, can conceal multi-generational pay streaks compressed by floods and seasonal flows. Use a pan or sluice and observe material behavior. Gold will settle fast, hugging the bottom. Garnet and ilmenite will lag just behind. Quartz, being less dense, may remain longer in suspension, but when it appears in the same riffle pocket as the others, especially in the final inches of the sluice run, it marks a specific flow profile, one where multiple density classes reached equilibrium. That's rare and valuable. The geometry of these deposits matters. In diamond-bearing alluvial fields, like those found in parts of West Africa or the Colorado-Wyoming craton margins, diamonds can be trapped in similar tailouts, but require slightly different mechanics. Diamonds are both dense and hard, but their shape, often octahedral, makes them prone to ricochet and skip along bottom surfaces before settling. When you find quartz with rounded pyrope garnets and subangular ilmenite in the same bend, you may be looking at a remnant diamond trap. Even modern riverbeds can mask paleo concentrations. During heavy flooding, river systems often cut new channels, leaving behind buried terraces. These are often invisible from the surface but show up as subtle humps or changes in vegetation. In these old channels, quartz-rich lag deposits often persist above real pay streaks. Digging a test pit or trench in such areas can reveal multiple layers, new gravels above, ancient concentrates below. Don't forget the upstream implication. If you're seeing angular, stained quartz settling with heavies in a bend, it hasn't traveled far. Unlike rounded, pure white float from distant erosion zones, these fragments signal active release from a nearby vein or pipe, possibly within a few hundred meters. Every sample pan in this context becomes directional data. The presence of quartz in these deposition zones narrows the map, but it also raises a question. Among so many lookalikes in the field, how can you quickly sort which quartz samples matter? The next step isn't about origin, it's about reading the sample itself under 10x. Because once you learn the signs, even the smallest fragment can unlock a pattern. There's no lab in the field. That's why the 10x loop remains one of the most critical tools in any prospector's kit. With it, a simple piece of quartz becomes a document. Layers, inclusions, fractures, and surface textures tell a history that rough observation misses. And when you're tracking gold or diamond indicators, these microscopic features separate signal from noise fast. Start with clarity zoning. Quartz that formed in mineralized fluids rarely grows perfectly. Instead, it records pulses of heat and chemistry. Look for ghostly internal zones, slightly different transparency bands, faint clouding, or interrupted growth lines. These zones often record pressure shifts or chemical triggers that also cause metal deposition. Quartz from barren systems tends to be uniform, either clean or completely milky. But productive samples are rarely so consistent. Color adds another layer. Under the loupe, smoky quartz isn't just darker. It often shows patchy, inky concentrations. These may signal exposure to uranium-bearing fluids or the presence of radiation-heavy minerals nearby, common in granite-hosted gold systems. More importantly, reddish or brown halos around fracture lines often signal ion oxidation from sulfides. A good indicator quartz under magnification will rarely be pristine. It'll be scarred, healed, stained, or zoned. Signs of life, not sterility. Now inspect contact textures. Are other minerals visible within or on the quartz? Tiny inclusions of tourmaline appear as black needles, usually aligned. Pyrite shows as reflective cubes or irregular brassy flakes, often caught in healed fractures. Garnet can be harder to see, but small dark red grains lodged at contact points or inside microcavities give it away. Even ilmenite, black and slightly metallic, sometimes occurs as platelets or fine grains caught in quartz microfractures, especially in diamondiferous zones. Field quartz with visible contacts like these deserves immediate retention. Mark it, GPS it, and compare it with surrounding float or vein material. If several samples from a small area show the same inclusions or zoning style, you're likely near a shared source, whether a quartz sulfide vein, a Grisen pipe, or a weathered kimberlite contact. Texture matters too. Under the loupe, sugary quartz, granular and sparkly, often indicates low-pressure crystallization, typical of epithermal or upper-level systems. In contrast, massive quartz with fluid inclusion trails or wormy growth patterns might reflect deeper emplacement, closer to magmatic sources. Such textures correlate with higher potential for associated metals or volatile-rich environments capable of transporting diamonds. Finally, watch for pseudomorphs, minerals replaced by quartz but retaining original shapes. A cube-shaped cavity in quartz where pyrite once resided tells a different story than a smooth, homogeneous mass. These ghost structures signal chemical swapping during fluid alteration, often within zones of strong mineral mobility. One field trick: scratch the surface lightly with a steel pin under magnification. If the scratch reveals a darker interior or causes a metallic inclusion to reflect, you've just confirmed the presence of a sulfide or heavy inclusion, key for gold association. Always rinse samples in clean water first. Dirt can mask or mimic real features. At this stage, you're not guessing. your screening. Visual triage allows you to eliminate barren quartz fast and preserve only those with meaningful inclusion, zoning or contact traits, but occasionally a quartz sample throws a curveball. Heating in sunlight reveals thermal gradients, or a simple hot rock test suggests deeper secrets. The next step goes beyond optics. It's about how quartz responds, not just how it looks. Under direct sun or near a warm surface, most quartz warms slowly and evenly thanks to its low thermal conductivity and internal uniformity. But certain quartz samples behave differently. They heat patchily, retain warmth longer on one side, or even develop condensation on only part of their surface when exposed to cool air. These thermal anomalies are subtle, but they signal internal complexity and often hidden mineral companions that matter. The reason lies in inclusion behavior. Quartz with metallic sulfide threads, iron oxides, or dense mineral cores like magnetite or ilmenite doesn't transmit heat the same way as pure silica. These inclusions create localized heat sinks or retainers, causing uneven surface temperatures. In the field, you can detect this by warming a sample in your hand or placing it on a sunlit rock, then holding it against your cheek or forearm. One side may feel warmer, or temperature may linger longer than expected, especially if dense inclusions are just below the surface. While not definitive, this test acts as a fast field filter. Uniform quartz without conductive inclusions cools rapidly and evenly, but quartz that holds warmth asymmetrically may contain trace elements that warrant further investigation, especially when combined with visual signs like zoning, staining, or inclusion trails. In diamond terrains, this test becomes more subtle but still useful. Kimberlite float, or contact-altered quartz, sometimes contains ferromagnesian inclusions, tiny specks of olivine, chromite, or serpentinized fragments that alter heat response. A sample that feels denser than it looks and also warms irregularly. Under sunlight could be a hybrid indicator, quartz that formed at the edge of a mantle-derived intrusion. The test can be enhanced with a handheld thermal imaging camera or even a sensitive digital thermometer. Place several quartz samples side by side under identical sunlight exposure for a fixed period, say 10 minutes, then compare surface temperatures. Consistent anomalies in one or more samples suggest non-silica material inside, pointing toward metallic or mineralized inclusions. It's a modern refinement of a centuries-old tactile test, but even simpler cues matter. After thermal cycling, heating and then exposure to cool air, observe condensation. Some quartz samples develop light fogging only on one face. This is especially noticeable on quartz with surface porosity or microfractures, often a result of hydrothermal shock. In gold zones, quartz exposed to multiple episodes of heating and cooling tends to fracture internally, leaving stress lines that subtly affect its thermal signature. The value of the thermal test isn't just in detection, it's in differentiation. When two pieces of quartz look similar under the loupe but behave differently under heat, you have a reason to split your sample pile. This is particularly helpful when prospecting in areas with widespread barren quartz float. Thermal behavior paired with inclusion analysis lets you discard dead weight early and preserve only what may lead to economic veins, pipes, or paleoplacer traps. Still, not all clues lead forward. Some quartz samples pass all these visual and thermal filters and still yield nothing. Why? Because in some systems, size itself becomes the trap. The next common misread flips expectations. Why the biggest? Cleanest quartz boulders might be your most misleading find. It's a counterintuitive lesson that catches many in the field. The most striking quartz, large, clean, and gleaming, is often the least valuable. Massive quartz boulders, especially those with pure white interiors and smooth fracture planes, tend to dominate outcrops and tailings, but when tested, they yield little to no economic mineralization. These specimens look impressive, but in mineralized systems, their perfection often signals sterility, not promise. Here's why. Quartz forms in a range of geological environments, but massive quartz typically develops when silica-rich fluids cool slowly in low-pressure zones with minimal chemical complexity. These are the drain lines of a system, places where fluids have already offloaded their metal load upstream and now only carry dissolved silica. As pressure and temperature drop, that silica precipitates in volume, forming thick veins or pods of near-pure quartz. No inclusions, no sulfides, no heat spikes, just barren filler. Such quartz often occurs in late-stage emplacement after the main mineralizing pulse has passed. It seals cracks, fills voids, and overgrows earlier mineralized zones. While it may contain ghost structures, traces of earlier minerals, it rarely hosts new metal deposition. The result is what many call bull quartz, big, bright, and misleading. In the field, massive quartz can dominate terrain visually. In some greenstone belts or alpine quartz ridges, entire slopes are littered with boulders of white or slightly bluish quartz. These often draw prospectors into digging, hoping for hidden veins or buried feeders. But unless the quartz shows staining, inclusions, or adjacent alteration in wall rock, it's likely part of a barren cap. Worse, it may sit above truly mineralized systems, blocking access or diluting sample assays. There's also the shape to consider. Massive quartz tends to fracture conchoidally, curved shell-like surfaces without much angularity. Its break is glassy, its density predictable. Compare that to fractured, iron-stained or sulfide-veined quartz, which breaks irregularly and often reveals contrasting textures or mineral inclusions on freshly exposed surfaces. In diamond terrains, massive quartz is even more misleading. While its presence in ultramafic zones may catch the eye due to contrast, it often comes from surface silica remobilization or unrelated hydrothermal overprinting. Diamond indicator. Minerals, like chromite, pyrope, or ilmenite, rarely coexist in massive quartz bodies. If anything, their absence from the surrounding concentrate is a sign that the quartz may be masking a different geological history altogether. So why not ignore large quartz altogether? Because its presence still provides context. It can mark structural weaknesses, old fault lines, or fluid pathways. These zones might have once hosted mineralizing fluids. The trick is to test edges of massive quartz bodies where smaller veins, breccias, or contact zones may tell a different story. Use a combination of tools: magnet sweep to check for magnetic sulfides in fractures, UV light to test for fluorescence, often absent in pure quartz, and weight in hand to detect subtle density changes. If a boulder seems unusually heavy for its size or displays a temperature anomaly under heat, it may contain hidden sulfide pockets. Ultimately, massive quartz isn't a villain, but it is a filter. When you see it, shift your attention to the margins, the fractured zones, and the mineralized wall rock, because in certain terrains where quartz is rare, its very presence becomes a paradox. And that's where we go next, into the ultramafic, zones where quartz doesn't belong, unless it's riding shotgun with diamonds. Quartz is almost alien in ultramafic terrains. These mantle-derived rocks, rich in olivine, pyroxene, and serpentine, form in high-temperature silica-poor environments. So when quartz appears in these zones, it's not by accident. It signals either late-stage hydrothermal invasion or contact with felsic rocks, both of which open the door to something much rarer, the possibility of diamond-bearing systems. Kimberlite and lamproite pipes, the primary carriers of diamonds from mantle depths, intrude through ultramafic domains. These pipes are typically soft, weathering into clay-rich soils that erode easily, but they often alter the surrounding rocks through heat and volatile release. In such contact zones, especially where fluids migrated along fractures or fault intersections, quartz sometimes precipitates as late-stage gangue or as a remnant from earlier crustal fluid pathways. When you find quartz fragments in serpentinized terrain, especially near chromite, ilmenite, or magnetite, you need to slow down. This isn't a common combination. Ilmenite and magnetite are strong diamond indicator minerals. Their presence, especially in rounded but high-density forms, often marks erosion from a nearby kimberlite or lamproite body. If angular quartz appears in the same pan or slope cut, it's not just background, it's a marker of fracture reactivation or hydrothermal overprinting at the edge of something deeper. This convergence is rare but powerful. In parts of the Wyoming Craton, isolated quartz float has been found on ultramafic ridges, near diamond-bearing indicator trains. In Siberia's Mirny field, diamond indicator minerals have been recovered from weathered ultramafics with quartz, stringers nearby, believed to be from post-intrusion hydrothermal events. The key is reading both mineral association and structural context. Look for quartz that's different, smoky with iron staining, or with included dark grains that respond to magnet sweep. These samples often form in localized fracture fillings, thin, veins, tension gashes, or breccia zones where fluids found escape routes during pipe emplacement. While these quartz zones may only be centimeters thick, they mark the pressure pathways that brought diamonds closer to surface. In some cases, the quartz acts as a carrier, not of diamonds themselves, but of the geochemical fingerprint of the pipe. Trace elements like nickel, cobalt, or chromium can lodge in quartz through inclusion of serpentinized olivine or tiny chromite particles. These inclusions are not visible at a glance, but under magnification or later lab assay, they can confirm proximity to an ultramafic-hosted system. Safety here becomes a factor. Ultramafic zones often weather into slippery clays and can be unstable underfoot. Additionally, they tend to be remote and poorly mapped. Fieldwork in these regions requires attention to slope stability, sudden weather shifts, and wildlife presence. But for those prepared, these zones offer the rarest conjunction, quartz as both signal and anomaly, evidence that something unusual breached from below. Now, you need to capture that evidence, concentrate it, sort it, and separate what's worth keeping. That means setting up a system that doesn't just wash material, but also tracks what concentrates with quartz in each run. Because the real test of quartz as a pathfinder comes next, in the sluice, where heavy logic begins to apply in the GI. Field, the sluice isn't just a tool, it's a filter for the truth. It lets gravity do what eyesight can't, separate material by density, shape, and hydrodynamic behavior. When quartz appears in the final concentrate side by side with heavy indicator minerals, it confirms more than proximity. It defines flow convergence. And in diamond and gold prospecting, convergence zones are where theory becomes discovery. A standard sluice system, properly tuned, allows fieldworkers to concentrate materials ranging from coarse gold, SG 19.3, to magnetite, ilmenite, garnet, and even dense quartz varieties, SG 2.6-2.9 for typical milky quartz. The setup must be deliberate. If the angle is too steep or water velocity too high, lighter fractions, including promising quartz fragments, flush out. Too flat, and the system overloads. For mixed material targets, like gold and diamond indicators, a 4-6 degree sluice pitch with consistent flow is optimal. Start by classifying material to a consistent grain size. For indicator mineral work, the 20 mesh 0.85 mm is a common benchmark, while number 40 mesh 0.425 mm helps isolate finer heavies. Run these separately. Comparing results by fraction size allows better inference about transport energy and concentration. Layering. Quartz fragments retained at finer mesh sizes, especially when co-occurring with pyrope garnet, chromite, or gold flakes, signal source convergence. The key is what lands in your final trap. If you're seeing quartz fragments with sharp edges, minor staining, or visible inclusions nestled among black sands, ilmenite grains, or deep red garnets, you're not just in a high-density drop zone, you're near a multi-phase release site. It suggests that gold diamond indicators and silica ganglier are eroding together, which rarely occurs unless a vein or pipe system is actively shedding upstream. Field notes are essential here. Mark exactly where each sluice run is drawn from: elevation, slope aspect, proximity to bedrock breaks, and any visible quartz float nearby. Over time, mapping these returns reveals high probability corridors, where heavies and quartz overlap consistently. These corridors often trace back to structural features, fault jogs, intrusion contacts, or paleochannel scars, places where mineralization pulses intersected transport vectors. In diamond terrains, sluice returns get even more granular. Pyrope garnets and chromite may be missed visually, but can be recovered magnetically or by their color luster combination. When these appear with quartz chips, especially smoky or fractured ones, It suggests that erosion of the kimberlite source also intersected crustal fluids. In this sense, the sluice becomes a geological time sorter, capturing products of both mantle intrusion and surface remobilization in the same tray. Field variation matters. In some zones, quartz fragments concentrate upstream of heavies. In others, they appear downstream or only in secondary traps. This positional behavior provides clues about local gradient, turbulence, and boulder configuration, each of which affects where values drop. Observing whether quartz consistently precedes, follows, or coincides with heavy mineral concentrates builds a behavioral model of the system. Finally, sluice design should allow for staged collection. Modular riffle systems or nested matting. Zones allow you to segregate material by drop point, early heavies, midstream concentrates, and late lights. If quartz begins appearing in the same trap section as gold or pyrope, it validates the gravity window you're targeting. A single overlap like this may be anecdotal. 3 or more across different samples. That's a pattern, and it points upstream. But what if the weight in hand doesn't match the visual expectation? What if something looks like quartz but feels wrong? That's when you turn away from gravity and toward your own senses, starting with the oldest and most direct of field. Checks the weight test. Because in some places, what walks like quartz isn't quartz at all. Hold it, literally. A piece of quartz pulled from the pan may look right, milky, angular, perhaps even stained, but if it feels too light or too dense for its size, trust your instinct. Weight in hand is a field test older than geology. Degrees, and when done with enough reference, it can expose quartz mimics and spot heavy value float before the first assay. Standard quartz has a specific gravity, Sg, of around 2.65. That means it's significantly heavier than most host rocks. Like shale, sandstone, or feldspar, Sg 2.6, but much lighter than heavy indicator minerals like magnetite, Sg 5.1, ilmenite, Sg 4.7, or garnet, Sg 3.5 is 4.3. Gold, of course, is in its own league, over 7x denser than quartz. But the key value of this test is to detect quartz lookalikes that fall outside the expected range. Start by training your hand. Carry known pieces of milky quartz, feldspar, and magnetite with you as field references. When you pick up a suspect fragment, compare the heft. If it feels heavier than quartz of similar volume, it may contain metal oxides, dense inclusions, or be an entirely different mineral, perhaps chalcedony, jasper, or even weathered corundum. If it feels light, porous, or brittle, you might be dealing with opal, tuff, or rhyolite, a distinction that matters greatly when tracking hydrothermal indicators. In diamond-bearing zones, this test gets sharper. Some quartz-like float is actually chalcedonic silica with embedded pyrope or chromite. These will feel subtly denser, closer to 2.9 or 3.0 Sg, while still passing as quartz to the eye. In contrast, weathered kimberlite nodules can masquerade as quartz until lifted. Their lower density, Sg 2.3, 2.5, often surprises the hand and points directly to the soft ultramafic matrix that delivered diamonds. If something looks quartz-like but feels light and crumbly, test it with water displacement or simply try to fracture it. True quartz will resist steel. A disguised kimberlite nodule will powder or chip easily. In placer contexts, weight separation becomes even more valuable. When you pan a mix of quartz and indicator minerals, how they settle underwater tells a secondary story. If two fragments of equal size behave differently, one sinking quickly and one hesitating, there's a density difference worth noting. Some prospectors create makeshift float buckets, placing quartz fragments in water and timing their drop through a column. Fast sinks tend to carry heavier inclusions or be imposters entirely. The lookalikes are numerous. Feldspar, especially. Albite or orthoclase can mimic quartz in both color and luster, but it cleaves differently and feels lighter. Opal, while technically a form of hydrated silica, is often less dense and may appear waxy rather than vitreous. Chalcedony and jasper can both present as colored quartz variants, but their density varies with iron content, and that's often a hidden clue to system chemistry. For in-the-field confirmation, carry a piece of SiC sandpaper, 0.9 hardness. True quartz will scratch glass and resist the sandpaper. Feldspar and most quartz mimics will show wear or yield a powdery streak. Even a quick rub against an unglazed ceramic tile can help. True quartz leaves little, but hematite-rich imposters leave a red streak, and manganese-rich rocks may leave black. This weight test, combined with texture and color, becomes a fast triage method. Keep what matches quartz by look and heft, but elevate anything that feels denser than expected. That fragment may not just contain value, it may be value in disguise. Still, even weight can deceive. Some kimberlite float weathers to look exactly like quartz from the outside. That brings us to the next deceptive twist in the trail: how eroded pipe float can impersonate quartz, and how to tell when your prize is just a skin. In diamond country, nothing wastes more hours than a kimberlite float that looks like quartz but carries no weight and no value. These imposters are common along weathered pipe margins, where crumbly surface rock hardens into pale fragments that mimic the luster and break of milky quartz. To the untrained eye, it's a lucky strike. To the seasoned field worker, it's a trap. Kimberlite pipes are volatile, rich intrusions from deep mantle, often brecciated, altered, and soft near the surface. When weathered, their clay-rich matrices break down quickly, leaving behind resistant fragments that undergo surface hardening, especially in arid climates or areas with silica mobilization. These chunks can take on a pale cream or bluish-white color, sometimes with a rough conchoidal fracture that resembles quartz nodules. In some terrains, the resemblance is strong enough that even experienced hands toss these into the vein quartz pile. But a few simple checks unmask the difference. First, look at texture under magnification. True vein quartz shows crystalline microstructure, tiny interlocking grains, growth zoning, or healed fractures. Kimberlite float, by contrast, often appears duller when freshly broken, and under 10x may show pseudomorphs of olivine, phlogopite flakes, or soft clay alteration, halus. These are not quartz traits, they're signals of ultramafic parentage. Second, test for hardness. Even weathered quartz resists scratching from steel. Kimberlite float doesn't. A light stroke with a knife point or SiC sandpaper should leave the surface untouched if it's real quartz. If it powders, scrapes, or dents, it's not quartz. It's altered mantle material, possibly a weathered xenolith or carbonate-rich breccia. Third, weight and magnetism. Quartz has predictable heft, but some kimberlite fragments, especially those rich in ilmenite or magnetite, feel heavier than they look. Their magnet sweep over such fragments may produce a weak pull, especially near embedded grains. Others feel oddly light for their size, particularly in hydrated, clay-altered zones. These outliers are key. They mark proximity to a weathered pipe. Margin, where diamonds may have once concentrated before weathering stripped them downstream. One overlooked cue is reaction to moisture. Splash both real quartz and suspected kimberlite float with water. Quartz will bead and stay slick. Kimberlite float often absorbs moisture unevenly, darkening in patches or turning chalky. This porosity signals alteration and clay content, not properties of hydrothermal quartz. In regions like Angola, Yakutia, and parts of northern Canada, field teams use portable XRF to confirm magnesium and chromium spikes in quartz-like float. But even without instruments, visual and tactile diagnostics can build a credible case. Quartz imposters tend to cluster near known or suspected pipes, often within 200-500 meters of center. Mapping these clusters reveals erosion patterns, which, combined with indicator mineral trains, can point to the source vent, and that's the pivot. These mimics are still valuable, not for their intrinsic worth, but for what they reveal. If you find quartz-like float in a known ultramafic zone, and it fails hardness or luster tests, don't discard it. Map it. These fragments may be remnants of surface erosion from a pipe that's now buried under soil, river wash, or basalt cover. The intersection of quartz float and diamond or gold indicators isn't universal. It thrives in specific geological contexts. And while quartz occurs everywhere, Its diagnostic reliability peaks in ancient, structurally complex terrains where fluid movement, tectonic activity, and deep crustal plumbing systems have overlapped for hundreds of millions of years. These are the shields and the belts, the old bones of the planet. Cratonic shields such as the Canadian Shield, the San Francisco Craton in Brazil, or the Kapval Craton in southern Africa are prime ground. These ancient continental cores host the structural stability required for diamonds to survive transport from the mantle, and the deep fractures needed for kimberlite or lamprite pipes to rise. Quartz here appears in two forms: vein remnants near shear zones, and silica overprint from hydrothermal breccias that often follow fault corridors. In the Canadian Shield, especially around the Slave and Superior provinces, quartz float enriched. With ilmenite and pyrope, has been found downstream from eroded kimberlite pipes. Here, quartz isn't a direct diamond carrier, but its shape, context, and mineral companions indicate proximity to structurally guided intrusion points. Field crews map quartz float trails in tandem with garnet and chromite dispersals, allowing reverse vectoring toward buried pipe sources. Greenstone belts, such as those in Western Australia's Yilgarn Craton or Tanzania's Lake Victoria region, also show strong pattern compatibility. These belts host multiple generations of deformation, allowing mineralizing fluids to pulse repeatedly through fractured rock. In these zones, quartz veins form not just once but episodically, creating composite lodes enriched with gold, sulfides, and secondary indicators like tourmaline and almandine garnet. Where these belts are but ultramafic or serpentinized zones, you gain the rare overlay of gold and diamond indicator logic,